So we have time.
Would you take in the IUCAA? We'll
take them later.
Take them or tomorrow.
Yeah. This?
It's okay.
So that's people online.
Okay, so good afternoon, everybody, and welcome to the colloquium of today. Today we have a very special guest speaking for us. So, Dr. Vadim Burwitz from the Max Planck Institute for Extraterrestrial Physics in Garching, Germany. So he did his PhD thesis many years ago on the series, actually from Göttingen, and then he moved to MPE thereafter and built his expertise on testing and calibration of X-ray optics, and now he is the head of the test facility at MPE, which is PANTER for the last 2 decades almost, and has been instrumental in calibrating almost all the X-ray mirrors and detectors that has flown in X-ray astronomy, starting from Chandra, XMM, eROSITA, Einstein Probe, and also the next generation missions. So I'm very excited to welcome you here and listen all about it. Thank you, Vadim.
Okay, thank you very much for this nice introduction, and you can switch it off.
You have your own.
Okay. So it's a pleasure for me to be here. It's been now 8 years since I was here last. Last time I was here, there was a big IUCAA calibration meeting, and I got to meet many people in the community. Fortunately, I haven't been back since then, but now I think it'll become more intense because there's many new projects in India also coming up. I think we can help on that. And so basically, yeah, I'll tell you a bit about what we do and what we can do to also support the community here. And basically, this is the heritage of our facility. So we've been involved worldwide in developing, testing in X-rays, environmentally, vibration, thermal cycling, and calibrating X-ray optics, detectors, and complete telescopes when we can fit them into our test facility at the same time we try and do that. and that's been ongoing for the last 50 years. I've only been involved in the PANTER facility for the last 20 years, the last 15 years as head of the facility. And so it's very exciting. We can do a lot of things. And yeah, this is the team we have. We're only, as you can see, 7 people. An 8th person's only very short, twice, 2 days a month. So these are people who do all the work. So we have, including myself, 4 scientists, engineer, and a technician, and that makes the magic. But we have the support of all the workshops and electronics and engineering departments of MPE. So let's do this here. Brief history. Nobody's supposed to read everything. That's why I highlighted the missions here. But it goes back really to the mid-70s, where a small facility was built. And then we also tested optics for rocket experiments, exosat. Then for ROSAT mission, we prepared things. 1982, long beamline came to be. I'll be showing pictures in a moment. Then we added a big chamber so that ROSAT could fit in, tested SACs. Also tested solar experiments, SOHO, the SOHO CDS experiment. Then in the 90s, things became even bigger. Introduced, prepared the calibration for XMNU. A whole new building was built up. Our existing chamber was doubled in length to 12 meters. We also provided optics for ground-based experiments here, like CAST, which is a solar axion telescope. Then we tested that, and that was using the same optics that was on the Brixus mission, which would have been a predecessor to eROSITA, but fortunately didn't work when it launched. And then here's what we did do is 2002. I wasn't part of the team at PANTER yet, but I've been using PANTER for Chandra measurements as a user, back then. But we had the whole SWIFT telescope in the facility. It was flown in on a military transport machine. It was trucked from Frankfurt to the airbase to PANTER, put in, we tested, and shipped back to America, and then launched. We did many important tests were done back. Then in 2004, future projects were on the horizon. SUS, gigantic telescope, 10 square meter collecting area. The technology lived on, but as IXO, which you can see down here, NewAthena. So things that are purple aren't working anymore. Mission life over. And blue is missions which are still active. Green are missions to come or were going to come, like the 20-meter focal length IXO telescope, which then was converted into Athena and now is NewAthena. So that was just part 1. And here, let me just get this right. I've got it set up here. So here we go from 2012. That's since I've been involved. We've did all the acceptance and calibration of 8 mirror modules for eROSITA. We tested the hard X-ray telescope, modulating telescope for the Chinese. Then we have the SVOM optics, which we tested, and the actual whole telescope inside our chamber. That went on for 7 years. Then we've been testing with the Americans also many projects which were going to be coming, ARCAS. Then in 2019, a very interesting mission came, Einstein Probe. That was a very fast mission. It was approved 2018, and then from 19 to 22, we did everything. And it was launched not too long later. And then we have basically little rocket experiments, OGRE, eXTP, which is a future mission coming, NewAthena. Then we have special mirrors for test facilities for Beatrix and Vertex. AXIS is a NASA probe mission, and then now we're coming along the line to testing sort of pre-production optics for NewAthena. That starts this year. So we're always busy, but full of interesting things. And I hope to at some point in the future also be able to name some Indian experiments in optics that we test for future. So a lot of introduction about the facility, history and all that. How do X-ray telescopes work? I don't know if everybody's aware of it, but X-rays only reflect well under grazing incidence. That means angles smaller than a few degrees. And therefore, our mirrors aren't like these concave mirrors we have in the optical or infrared or UV, but we have these. This is a cut through the mirror, so you have all these cylinders, which are divided into two parts. The front part, which is parabola, and then hyperbola. Paralight reflects one, second focuses. This is the classic mirror for most of the missions we have, except for the very wide field images, and for that we use a technology called lobster eye optics, and that's also been flown now, and they work very well. And so there you have a nice curved optic with lots of parallel channels, basically channel plate, and then the different parts only focus on light into small areas. So these are limited in effective area just by the design. And wait a sec. There we are. Here we have the zoom of all the different types of optics which exist for X-ray telescopes. And from left to right, we go from usually from very heavy, very high quality mirrors to very to about here, where you have high collecting area and lower spatial quality. So your point spread function is much larger. But for doing fast timing, doing large area imaging, so surveys, they're good enough. And on the left-hand side, you have down here at the bottom left is Chandra mirrors. Those are the best mirrors that have been made to date. They're thick pieces of glass, very heavy, but individually polished mirrors, primary, secondary, and they produce half an arc-second image quality, which is something comparable to normal optical telescopes. So that gives you a good idea how to relate what you see in the optical with the X-rays. All the other ones are optimized for gathering more X-rays. So here's XMM, here's eROSITA, there's where's it down here? JetX mirror, as like on board for Swift. Then you have NewStar optics and IUCAA optics. These are slump glass optics, which are then coated for high energy experiments. And you see what I've framed in red are optics tested with PANTER. But what was interesting, the last week being here in India, I've discovered that there's a lot of work already going on in the development of X-ray optics. And so there's groups working also on electroform nickel optics, slump glass, micropore lobster eye optics, and even Kirkpatrick, Baez, or Schmidt type wide angle telescopes. So there's a lot of work that's been started and it's going ahead. And yeah, so there's a lot coming in the future. So my X-ray test facility looks like this, as seen from the air. It's a 120-meter long tube. In this hut here, we have an X-ray source, which is basically our artificial star. We just have some pumping houses where we generate a vacuum of 10 to the minus 6 millibars in the tube. And down here, there's some big pumps. There's a gate valve over here, which separates the tube vacuum from chamber vacuum. In here, we have a big chamber, 12-meter long, 3.5-meter diameter. And there we can put our experiments, our optics, our detectors. And this is the baby I have to look after, make sure it works nicely and delivers good calibration. This just is a quick overview. So here I've got all the missions. I'll just zoom through it so you can see the optics are usually placed at different distances to the detector. The detector's down here. Sometimes we even have to push the optic into the tube on a special optical bench when they get too long. And then This is what it looks like. So this is for Athena 12-meter optics. Seeing the sources at 120 meters distant, it's a divergent beam. The image distance is not 12 meters, but 13.3 meters for these optics. And it's always a bit longer than the focal length. So go to 9-meter optics, 5-meter. These are all the different missions which we've been briefly mentioned, which we've recently tested. You see, this is a very, very short focal length. It's 0.3 meters. And this is an optic which they're also testing here in India, something similar to that. So, and then we can, for very long focal lengths, 20 meters, we can even put the optic in a big chamber here and have it focus, go through a tube out of the chamber and onto the detector. But these are all things we can do. And we can even make a parallel beam, which is quite fascinating with an X-rays. To make a lens or a mirror that's good enough to make a parallel, it's very difficult. So we had to resort to some tricks. And here we added a Fresnel zone plate, which in one of the orders, it has a focal length of 120 meters here, 122.8 to be exact. And then here it goes through, makes a parallel beam, illuminates an optic. So it's only a very small area that can be illuminated parallel. At only one energy. It's designed for 1.5 kV aluminium, and then it focuses it. And this is basically the result of a PhD thesis, the zone plate that was made. Very nice. And here you can see this will be the center of the zone plate, and this is the edge. And that's what creates the parallel beam. And it's a very nice bit of physics, because it's optics and physics. You get actually something good out. It's something which we use on a regular basis for testing smaller optics. For large optics, that's very difficult, yeah. So this is just the summary of all of them again. And here we go on to what is our artificial star look? A big jumble of cables, cooling systems, and basically inside this here, at the center, there's a little spot of 0.3 by 4 millimeters, which in projection looks like 0.3 by 0.3 dimensional X-rays. When you look at it from the main chamber, it's about 1 arc second. And that spot can be, you project electrons onto the anode, and those through Bremsstrahlung create Bremsstrahlung's continuum, and also characteristic lines depending on the target. We also have X-ray monochromators. So in the future, we're planning to go up to 100 kV if needed for some high energy experiments. Then we have detectors, because somewhere we have to get images of all these things, all these point spread functions, the effect, measure the count rates, the effective area. And here you can see what one of our detectors, this is a classic camera and integrating camera, where we've pre-aligned everything under air before we evacuate the chamber to a pressure of 10 to the minus 7 millivolts. And then here we have an eROSITA-like camera and a eROSITA-like demonstrator camera that was generated. And then we also have to measure the stability of our flux in the beam. We have a monitor count. And and all this data has to flow together and be used to then produce the analysis data which we need. Here, this is something, just to give you an idea, dimensions of the camera. It's 28 by 28 millimeters, 75 micron pixels. This is the same camera as basically is flying on the eROSITA and on Einstein Probe. Here you have a calibration spectrum taken with IUCAA, and you have then all 2 times the values of the titanium, and also the iron lines. And so basically we can cover the whole energy range in calibration. And what do we get from that? This is work where also Chandraji has been involved in calibration and the operations of eROSITA, which is at MP. We find that we have pretty good spectral resolution for these cameras, very close to the final noise limit. and also very good quantum efficiency. So basically, these cameras are very useful for doing all these on-ground calibrations. This gives you a sense of dimension of our chamber. So basically, inside this chamber, this is one of the biggest things we put. I think it's the biggest thing we put inside the chamber, which is the whole of eROSITA. And this was just 3 months before we delivered the whole system to Russia. We actually put eROSITA not only inside the chamber, but we had a special shroud, a cupboard, which could be then closed, and then we had heaters on it, and we had coolers inside it, so we could simulate the actual way it would behave in space. So basically, the top part here could be cooled with liquid nitrogen, where the radiators, you can see up front here, opposite them we had radiators cooled with, shrouds cooled with liquid nitrogen, so that it was behaving just as if it's in space. The only thing is we didn't test the optics with our X-ray source because telescope cameras have a cooling system, which we were also testing during this test. And that only works when it's perpendicular to gravity spacecraft, the whole payload, it's the telescope. Because this whole thing you see here was then taken to Russia and mounted onto the satellite. And so that was a cool test. Took us 3 months, so lots of tests. And basically all the hard work which we put into this over many, many years resulted in this image here. This is one of the first all-sky image taken with eROSITA, where we also have not only the German side, but also the Russian side in the image. But this half here of data is publicly available. And the nice thing is, I've also, at the conference I went to in Bangalore, I saw people have already downloaded it and have already been analyzing it here in India. And so anybody who's interested in X-ray sources from the eROSITA first sky service, there's a link to it. And if you have any questions, you've got the person sitting in the room here. So, and she knows lots of the details to be able to get things well. Nice. So, what else do we do? So we do many different types of optics. It's not just the whole space telescope, but we can test little optics like this one here. This is Lexi. This one was an interesting one because this one actually flew to the moon. It's on the moon right now. It was on one of these fast payloads which the Americans made. And they were only active for a week, and then they're just sitting there now. And then these are here. This is how we tested the eROSITA mirrors and Einstein Probe mirrors. So you have the mirrors here, you have masks in front, you have the detectors in the back, and all at the right distances. And we had here the wide field optics of Einstein Probe, which the Chinese group sent to us for testing. And one of them was the QM. QM was also launched as a separate test set. And we have Athena silicon pore optics, which are these little blocks down here. Shows a small images just now. Big prototype Kirkpatrick Baez. And here's a little telescope module, which is actually being launched as a CubeSat. And here's a parabola. This is a synchrotron-like optic. So they're very long, very thick, and very precise. And basically, this is the opening entrance window here. It's a very small slit where the light comes in, and it focuses the light at 2 meters distant. But this is going to be used the other way around in an X-ray test facility. So we're testing optics which are used to make parallel X-rays in the Beatrix X-ray test facility. And they put the X-ray source in the focus, and then the light comes out parallel of this. And then it goes through a complex set of quadruple crystal monochromator, not a double one, and then a beam expander, so they can make a very wide beam parallel X-rays. And here we go. Yeah, and this brings us back. I've mentioned them a few times just to give you an idea of what they look like. So you've got Einstein Probe, which has got 12 wide field imaging telescopes. And each one of these telescopes is actually 4 cameras and 4 sub-telescopes. So it covers a field of view of over 3,000 square degrees in one image. So each module is like 20 by 20 square degrees. And sitting at the center, fortunately, there are 2 telescopes which are identical to the telescopes on eROSITA. So the Chinese, we provide Chinese with the flight spare, eROSITA. ESA provided them provided money to have a second mirror module made, and the detectors we delivered. So basically, what the image of the detector I showed you up there, we delivered exactly that. Chinese, they made the electronics, the cooling, and so that worked very nicely. And of these, here you see these modules. Here is actually the test satellite that was sent up before Einstein Probe was set up. So at one point, we were finishing testing the optics, the QM optics, and then we get the frantic call from our colleagues in China. We need the optic back as soon as possible. And we didn't know anything why they needed it back. But then eventually it turns out they needed it back because they had to mount it inside this little demonstrator satellite. And with that, they could actually do already 1.5 years before launching Einstein Probe, they were already testing pipelines on real data. And that actually managed to get a whole sky survey, very shallow, with this one optic that showed that works very nicely. So here you can see the center of the Milky Way. These are all the camera modules here, illuminating it in one shot. And this is here basically then the telescope, which is in the middle there. And the second one is SVOM, which is a transient gamma ray burst observatory, which also, similar to AstroSat, has included, in this case, an infrared or UV telescope and a small MXT, the X-ray telescope, gamma ray burst telescope, and gamma ray burst detectors. So there's a lot of stuff going on there. And yeah, you can see on the left, we've got all the different campaigns that we did. So it's when we test an optic, it's not just one campaign. You test the QM optic, you test the FM optic, you even test the flight spare optic, calibrate, so that you know exactly what the performance is when you deliver it. And then we actually even tested the full flight model. We did a demonstration test here using the QM optic and the EM camera. And then we actually tested the flight module and the flight camera before it was actually then returned to France and then delivered to China for integration. And it was successfully launched in June 2024. And this is what it looked like in PANTER. So you have all these micropore optics, so it's very wide field of view. These are 1.15 meter focal length, so the field of view is not it's only a degree compared to 20 degrees. But it's because they wanted to follow up and localize where the objects are landing. And then here you can see there's the tube in PANTER where the light comes out from the X-ray source. Here we can see the detector on the back side. This is the detector seen from the front, looking into the integration room. This is basically from the side. So there's really a lot of work going on there. And then this is the flight model test. Actually, no, this is the QM test, sorry. And then the flight model test. And here you can see also all the flight electronics, which were tested in vacuum at the same time. So we actually were sitting in the control room at PANTER, and it's like controlling the telescope in space. And it allowed us to also debug the problems and issues. And that's why what makes it really exciting doing these things, and also very helpful for the teams making these optics. Then Einstein Probe, there was even more work to do, many, many more tests, vibration tests, cycling tests, and so on. And then we delivered it all then to China. So we had the FXT, WXT, and then it was launched. That was launched actually faster than SVOM, basically. Then here we have what it looked like in the chamber with the Einstein Probe optics. You have the FXT optics being tested, the wide field imager optics. And so taking one of these modules from the wide field imager, it was actually like calibrating 4 telescopes because we only had 1 detector. In orbit, they actually have 4 detectors, so it was easier for them for taking the data. But still, it was important to characterize each and every one of those sectors. And that is basically the kind of images we get. And this is what PANTER is all about. We want to know what is the point spread function of this? What's the half energy width? How does it change as you go from on-axis to off-axis? And you can see the central area, it's all nice and point-like. And then when you go further out, off-axis becomes a bit, looks more like a butterfly and extended. But that's the design, basically the result of the design of a Volta-type telescope, like I showed in the beginning. There's other designs which mitigate this a bit. But if you go to the wide field X-ray telescope, point spread function on axis and off axis looks identical. And that's because basically using the same type of optic, but from different angles. And so you get a very clean image there. But the difference is the PSF is much, much larger. So you have like few arc minutes as opposed to 20 arc seconds. And this very colorful image in the middle is very illustrative to how complicated and difficult it is to make one of these mirrors. This is an extra focal image, so the light has gone through the best focus and come out again. And what you can see here is actually the light collected by each ring. Basically, each mirror shell collects only a very small, thin ring of light. And that's what you see here. And then you can see that they wiggle about. They're not perfectly concentric. If they would be perfectly concentric, you'd have a best optic you have. But the reality is difficult because you have to glue these things. So you get all these little waves here. You can see here. So yeah, there's lots of things you can learn from this. The other thing which I mentioned is that you not only look at the point spread function, you want to know the efficiency. How well does a telescope work? How much light is collected? How many, and that, we usually talk of how many square centimeters of collecting area do we have at which energy. So the typical energy range is like from 0.3, 0.2, all the way up to, in this case here, for this optic, it's 5,000, but for other ones, we go up to 10,000 electrons, so to 0.2 to 10 kV. And here you can see the summary of all the measurements we did. So in yellow is the model, that's the prediction, and in all these 4 different colors is the measurements from the 4 different quadrants of a WXT telescope. And what you see here very nicely is the absorption edge of the coating of the material. And that's usually around 2 kV. For iridium or for gold, it's also shifted. But those are where we are. Then we go a bit towards the future. We're going to look at eXTP. And I'm just jumping a bit ahead. I got one of those 2 slides wrong. So we have future missions which we're supporting, we're working on. That's NewAthena, that we've been working on since the beginning of Athena, 2014. The optics technology has been 10 years earlier. They started at Zeus and for IXO. And this is what these optics look like. These are several test optics which we put into a structure to put in the vacuum chain. Here we were testing using the same technology also for Arcus. So one of the mid-X missions, which was unfortunately not selected, where you combine optics with gratings. So we're also doing tests with gratings. We're going to describe that in detail here. But then we have in parallel launch is 2037. It's actually 2038 right now, the schedule for Athena. So we're very interested in getting things happening earlier. There is a mission which was approved the year before last, end of 2024, which is eXTP. This is a Chinese mission. It's a timing mission, and it has basically 9 mirror modules, 3 for colorimetry, 5 for fast spectroscopy with STDs, multi-pixel STDs, and 1 for imaging. And this again has an eROSITA type camera and 5 STDs, which we are producing and providing to them. So that's basically it's a China MPE collaboration, not a China Germany, because on the official level there's not much going. So basically these are the science drivers for the timing and polarimetry, extreme density, gravity, magnetism, neutron stars, black holes, and basically you have all these key things which don't require high spatial imaging, except for the one camera, which we're telescope where we've added an imager. So that's why, and the effective area is large. Spectral resolution is better than 180 at 6 kV. So it's a big challenge, a lot of work. We do it. So if I go back here, let me jump back to the one skipped here. This shows you basically a demonstrator optic, which was produced by Medialario, Italy, for the Chinese group as a demonstrator. It's got 3 shells, 1 outer one, 2 very close to one another. You can see them here. Here's the tube, so we have to put it in. We have masks which you can move in to cover parts of the optic, so we can then study the one shell or the other one, because at this point we still have to learn how to make good optics and how to understand them well. And then forward to the calibration image. This image is shows basically 1/4 of the light which has been coming out of the telescope. And so basically, behind the black box here, that's where the focused image is. I didn't take an image there because it's very bright, but because I put my X-ray source on to be very bright, so that I could see all the contributions from the X-rays coming from the source. And so basically, I see here some direct light coming through. Here I see single reflections of hyperbola, of outer shell. Here are these wiggles here, some reflections which come off the parabola, the entrance side. And that's because we have a divergent beam. In a parallel beam, you wouldn't see neither the hyperbola image nor these other wiggles of the parabola. And then here you have overlapping 2 neighboring shells, which so you have the hyperbolas, and then you have here 2 grounds. And you see they're not perfectly round, and that's one of the issues which we in the next iterations have to then always address. So this just shows you the same but in more detail. But you can see that, for example, here, see there's lots of little lines. And this is a reflection of one shell. Basically, that tells you how perfect your parabola is. Your parabola should be a nice, smooth thing, but it's actually little waves on it. We're talking about nanometers, several nanometer waves, maybe 10 or 20 nanometers going up and down over millimeter ranges. And that makes it look like basically a record. So out of this type of measurements, you can also learn about the quality where things are going. So, and those waves can be measured also in the laboratory as waves in the surface of the optic. So this is, but scientists are not interested in what we were looking at a moment ago. They're interested in this. They want to know. They want the smallest HEW so that they get the sharpest images. They want to get the best spectroscopic resolution, and so on. And so basically, here we were testing all shells together, and the inner shell, the outer shell. And you see they're not perfect right now, because these were the first prototypes. But then when you overlap them, all these wiggles, they become more circular. And if you have 54 shells, you don't see the individual contributions, but they're still there. And the trick is actually for each shell to make this perfectly round. And then you get and have them overlap nicely. And then you want to study it at different energies. And then you want to measure how much photons are landing not only in the middle but outside, so that you can measure the scattering, see how good the surfaces of the mirrors are. So yeah, this is a very complicated graph if you're not used to it, but this is the effective area. Black is of all three shells measured together. In red, that's just the outer shell. No, blue is the outer shell. Exactly. In red is the two inner shells. And you see the waves go down. The effective area goes down for the outer shell at a lower energy than for the inner shells. And that's because your mirror angles under which the X-rays are coming in, the steeper the angle, and the lower the energy at which it still can get reflected efficiently. And so basically, the whole mirror module has 54 shells, or 58 in the case of 54 in the case of eROSITA, 58 in the case of XMM. This is only 3, but it just gives you an idea of a few things going on there. Then we can go one step further. For Athena, we want to look not only at how does a shell behave, an individual mirror module behave. So you have a small module this size, but to make an Athena mirror, you want to build a 2.5 meter diameter mirror module. So the largest mirror module that was assembled to date was the Chandra one, which was 1.2 meters, a solid glass rim. That's what, and seeing it was solid and thick, it was very heavy. And you could only make 4 shells because otherwise the mass was too much, and it would be a problem to launch, and also to make them was very costly. Because the original plan actually had foreseen 6 shells. They skipped 2 of them just because of launch mass. And so, and also a few other things, and they cost a fortune. And so for Athena, they said, how do we make an even larger mirror, which collects up to 1 square meter of light? We're talking about 1,000 square centimeters for Athena. For Chandra, we're going a factor of 10 higher. But we have to make compromises. We want to be lighter. Being lighter means you're not necessarily going to go down to 0.5 arc seconds. So the goal for Athena is 9 arc seconds. Then to make it lighter, you want to use materials that are very light. And so they came up with the idea to use silicon. And silicon is very light. But then how do you use the silicon and make good reflecting surfaces? So they took wafers from semiconductor industry. They're perfectly polished flat surfaces. And then they made grooves in them, cut out squares, bend them very precisely, and then they stack them. And then you get basically a little square like this here. It's difficult to see. I think I've got another image where you can see it better. But you need to then make lots of these modules. They're limited by the size of what you can bend and then mount between some holders. Then you mount them into basically these holes in a big 2.5 meter diameter structure. And we at PANTER, we had to then show together for ESA, we did some measurements. So we were given by the companies making this optic, they made sectors, basically a sixth of the mirror. If I get the whole mirror, I couldn't fit it in my chamber. It's too big. But if I get a sixth, that still fits. It just fits, and I can do a very nice test. And I can also then put in front of it and behind it shrouds where I can change the temperatures, simulate what happens to the optical alignment of all these mirrors, because each of these modules has to be put in here and co-aligned to make a nice perfect image. And then what we did is, if you look at this here from the top, you see the modules here. I haven't got the structure drawn in here, but here I have some shrouds, and then the X-rays are coming through to 3 of the optics. And for that, you may have to do a lot of designs and think of how to put it in PANTER. So this is where the optics are lying. There's the light coming from X-ray source. Here we have then basically the entrance to it. And then all of a sudden I had to add an extra chamber to my big chamber so that I could get from here to here 13.3 meters. Because my chamber is just too short. When they designed Athena, they should have made the focal length shorter. Then it would have been much easier for me. But they had their own ideas. So basically, this is what it looks like in the clean room then, the extra chamber added to the big chamber. So it's always a lot of handling big pieces of material. This is what it looks like in the little chamber. The back, you can see there's a camera. And this is the kind of image you get when you put into that big optic. We only put 3 little optics because it's an expensive process to make them at different positions on one radius. You'll see it in a second. And then each of those optics makes a little line. And they were purposefully not co-aligned, but they were just they were nearly was co-aligned, but it wasn't necessary because we always measured each one individually. And then we looked where the centroids, these little ellipses, landed when we changed the temperatures. Where do we go here? There we are. So this is what we had. We have them basically here 3 optics, the light coming through, focusing there and making this image. And then these images changed, the position changed as we changed the temperatures. And so you have to make very complicated structures and setups. And this whole thing, you can actually see the mirror structure in there. Gets very complicated. Then you have to wrap it all in multi-layer insulation. And then you have to bring all the structure into the chamber. Put a crane up here, lift it and bring it in. Everything is always like 5 millimeters here to spare, 5 millimeters there to spare. But it works. And we had to do this whole thing twice because ESA has 2 different contractors. So Airbus made a petal and Thales Alenia made a petal. And so we had to test firstly the one petal with the optics in it, and then we had to take it out of the chamber, remove the optics, you can, and then we had to put it in the other petal and then do all the same. So it was quite a lot of work. And now we're coming to the end of my talk soon, and it's about ground calibration ground facility cross calibration. So you see, we've done a lot of work at one facility, but how do we compare our data with other facilities? And that's where it's important for us to, on ground, not only work on in-orbit calibration and cross-calibration between satellites, it's important to, on ground, already have a good cross-calibration between facilities so that if I take a measurement at PANTER, or my colleagues in America take a measurement at their facility, Chinese at their facility, or in the future here in Bangalore when they have their facility, then we can then compare, take the same optic to one place or the other, and then compare the measurements. And make sure that when I measure it or you measure it, that we get the same results. And then we can make a good, say, prediction for the in-orbit verification. And so it's also important to make sure that we know that the optics perform as they should. And then when we go, here you can see, I promised you to see a nice picture of one of these modules. You see these different little pores here. They're the little tracks, channels, which have been cut out of the silicon wafers. So what's left over is only a very thin membrane of 110 microns. And the top side of the membrane is perfectly the shape of the mirror. And it's bent in this direction here. Basically, this is the curvature. So this optic here has a radius of 765 at the millimeters at the center. So you need like 48 of these optics to make one mirror shell, one ring. And at the same time, this is actually 38 layers and 38 layers. So it's exactly 76 reflecting surfaces. And that's what allows you to get a big effective area, with collecting area, with a light mass. Because basically the Athena mirror, when it's fully assembled and completed, will weigh 900 kilos. sounds like a lot, but an XMM mirror, which is made out of nickel, like I showed right in the beginning, that weighs 450 kilograms, and there are 3 of them on XMM. And so basically that's even more heavier than this scaling. So those are, and here you can see this is where the light goes in, and then you can see the light's coming out. There's the laser coming. So when we do prepare our setups, we always have an alignment laser shining through and comes through and then should focus on the detector. And here again are the tropic results for that. So these are different measurements we did on that. And also again, effective area of one module, 12 square centimeters. If you think back of the WXT graph I did, the effective area was like 2.5 square centimeters. So it's different optics have different optics modules have different efficiencies. And then here was, so this is one of the tests we did with the Chinese, where we actually used this test of this optic here, which I showed in more detail earlier, to do a cross-calibration between their facility and ours. They have what they call the mini PANTER, because I taught them when they were built, they said they were going to build it. I went there and we had lots of discussions. They came to PANTER to discuss what has to be done to get good calibration. So basically, that facility works very well, and we get very comparable results. So that's it. I have the measurements. That's a PANTER. So we're able to do a pretty good cross-calibration. So yeah, I'd like to come to the end here slowly and say that we have a very efficient logging facility, very flexible, where we can do lots of things. And most X-ray missions have been doing work, PANTER, being tested. Not all. There's a few which have. IXP hasn't. Just to name one. And some of the Japanese missions haven't come with. One of the Suzaku. And then done lots of work for recent missions, eROSITA, SVOM, Einstein Probe. And we've been also working on new missions, eXTP, Athena, Axis, Baby Axel. Baby Axel is another solar axion telescope based on a flight span mirror from XMM Newton, which has been in storage at PANTER for the last 25 years. And so we'll be able to be recalibrating that optic this year, July, planned, and then we'll be sending it to Hamburg, where it will be integrated into this solar axion telescope. And then that's mounted behind a long vacuum tube, which is surrounded by 1 Tesla magnetic field, has a 1 Tesla. But that's a very different topic. And then also helping new missions coming along and supporting testing and development of optics. And then, yeah, as part of this, all this work, we brought into life this new ground facility cross-calibration working group at IUCAA, which is the cross-calibration group where between missions, which has been running for the last 20 years. And we actually had good, lots of people here during the early phases of AstroSat, when we had the meeting here in Pune, which was great. That's why we also did the meeting. We wanted to get information into the system here so that we can get good calibration. And yeah, and also in case the cross-calibration is important, that if somebody has a mission and they have too many optics that have to be tested, that in case of emergency, somebody else who's got a facility doesn't have too much work to do, they can help out and give the same quality of results. And I think, yeah, these were just the goals for this cross-calibration. What we do, it's really taking one optic from one facility to the next, measure it, see what comes out. Another thing is to check if the ray tracing packages which exist all deliver the same predictions for the optics. So that means we'll design a generic optic which everybody puts into their software, and then we compare the results. And finally, just before final, is the analysis. How do we determine quality of the object, half energy width, the effective areas? How do we really do the analysis? And that's where we want to also then compare for the different groups who are doing this, compare how they do it and if they get the same results. Because that's also a very tricky thing, doing analysis, right? Especially when you then get to things where your point spread function becomes the size of your pixels and things like that. Then it gets really tricky. And then also then help with guidance of ground calibration cards for new missions. And like you just said, it was a nice colorful image of Bavaria, where we have our next gadget meeting, where all the sort of calibration issues that come up for new missions will be discussed. So I guess it's a very different talk I gave today than usual. I didn't show a single formula. Because I could show you lots of formulae, but I think the images give a bit of an idea, but there's so many details where one could spend hours talking. But it's to give an idea of what we have been doing, what we will do, and yeah, where we want to go, and we want to help also you guys here get new missions rolling and started. And so, thanks.
Thank you very much for this wonderful talk. We have a lot to learn from you. First, questions, please.
Very nice. So very nice talk. Do you also do off-axis characterization performance of the layers with the PANTER X-ray?
1 second, let me go back here quickly. I've got a nice picture here of axis. That's it there. Yeah, this is the off-axis images. So here in the middle, on the left, you can see this is really on-axis, and then here we go off-axis all the way up to 30 arc minutes. Basically, to the corner here, it's 42 arc minutes. And this is, and you can see how the PSF changes. At the same time, we also measure the vignetting function. So basically, at the center, you're 100%, and then as you go off, due to shadowing and aberrations and all sorts of things, you get then it goes down to maybe 50% at the edges. And so, and if you do this, and this is the same for the lobster optics, so the micropore optics, as they call it, you can see here it doesn't change. So you go, this is arc minutes off axis. So we're talking about 2.5 degrees, and it stays the same. And that's why they're able to take this wonderful image of the. I go back here to. There. Oops. Here you go. So here you've got this image, but you have a very uniform coverage of the sky over a very wide angle. So it takes them 12 images to get the whole sky covered at a very low count rate, but you're looking for bright, soft transients.
One more.
Yeah.
So one important thing is how well we know the effectivity, the accuracy at which we know.
The effective area is always a very tricky one to measure. And we also have to say we also measure the on-axis effective area and off-axis effective area. So that's what we can do here. Of course, the effective area is very tricky also because of the divergence. So ideally, I'd love to have a test facility with 1,000 kilometers length, but that's a bit wishful thinking. So I think 4 kilometers, if I could use to test the tubes for LIGO, that would be good. That would improve things, but I don't think they'll let me. Or let you. But maybe you can make a deal. And but then the X-ray source becomes very, very weak. Because basically it goes with 1 over r squared in intensity, so you have to have a very intense source to get it. But I do have plans in my tests, in my drawers at BE for building a facility with about 800 meters length. But that sort of didn't get funding from ESA because ESA had other ideas. And so I said, okay, I'm glad I don't have to put so much steel in place because it would only be for one mission. And the next big mission, there's none really on the horizon to require such a large facility. So I think for the sake also of the environment, it's good that it's not being built. And we can do a lot of work with the existing facility. And seeing it's been standing around now for 50 years doing a lot of it, it's a very efficient thing.
Yes, sir. You have, of course, the experience with the real mission. So,
Yeah.
how much typically is the change in the PSL from the cross-calibration to
Not bad. It depends, of course, on the type of optic you have. Because some optics are very sensitive. So with a chamber-like optic, you really have to be careful and very delicate. We're talking half an arc second. And there, any distortions through thermal, through gravity, can make an effect. But if you're talking like 10 arc seconds, it doesn't make that much of a difference. And the thing is, we made very, very good mirrors for eROSITA. And we got very good, very sharp images. But then when we launched it, we set the detector 0.4 millimeters intrafocal. And the reason for that was because we actually built a survey telescope. And because if you go back to that one image I showed here, it should come now. If you look at it, in the center, it's very nice, very small. But if I go 0.4 millimeters intrafocal, it'll still be okay. But all these points here will become better. And therefore, you're interested in the whole field, then you get a sharper image, average image for the whole. So we're not trying to compete with Chandra, we're trying to get a good survey image. And so those are the things you learn. But it's very important to know the precise position so that you can make those offsets. And starting with a good PSF, your final PSF will then also better. Thank you.
Thank you. Any more questions from the audience?
So I'm just curious about
So that the people online.
yeah, I'm just curious about your testing facility. Do you also design and assemble mirrors over there, or you just
We also did at NPE together with the Peter Friedrich, a colleague of mine. We also design and we also assemble things. A lot of the mechanical interfaces and holes and all that, that's all designed by us at the test facility. So basically, we're always talking with the different groups and what are their necessities, and we're also able to then adapt the facility to be able to get the best calibration at different energies, things like that.
And what is actually new about NewAthena? Because I was
New about NewAthena is very simple. It's got less effective area.
Oh, okay.
The PSF requirement is not 5 arc seconds; it's 9 arc seconds.
So it's like degraded version of it.
It's a question of cost. But basically, they came up with for Athena it was with 1.7 billion euros planned, and then New Athena is now going to, so for Athena, that's the numbers they came up with. And then they did a redesign, and came up with like 1.3 billion. With if they don't put so much effort into making sure that it's 5 arc seconds, so 9 arc seconds, and then yeah, so and also agreeing to having less effective area. So the ring is basically the design is made from 15 rings of optics, but they took out 2 rings. The structure could hold the outer 2 rings, but they're not currently they're not the baseline plan. But my feeling is that in the end they will put this. That's not going to be the cost difference.
And one last question. In your very last slide, you showed a comparison with Chinese facility. And there the effective area looked really high, like 50 or something.
Yeah.
So is this for a real telescope?
Those are real measurements from a real telescope. Exactly, 50 square centimeters. And that's only 3 shells. And imagine you take 3 shells.
So which telescope is this?
This is the prototype, the one I showed here.
Yes.
Okay.
This one here, basically. Here we only have 3 shells. Later on it'll have 50 shells. So we're talking about over 1,000 square centimeters there, much more.
So that's
Yes.
I have a couple of questions if there are none at the moment. So first, I'm curious about the thermal constraints for the mirrors for maintaining, I don't know,
The image.
the image quality. So for eROSITA, it's like around 20, right? So is it, I mean, does it depend on
This is the normal value which is taken by all machines. Reason being, that's the values at which the temperature range, plus minus 1 degree, at which we assemble it in the laboratories. So basically, that's the constraint.
Okay.
And then, of course, it depends on how well you can do thermal baffling in front of the mirror. And also in orbit, what we do have is the possibility to switch on heaters to keep the optic at the right temperature. So we have control systems in orbit which allow us to maintain that the mirror remains at that temperature. But you always have to then design it so that it depends also on how agile your telescope is. If it's moving around a lot, it's looking more towards the sun or looking somewhere where there's light heat coming in. So, but normally in the case of the eROSITA, for example, you have the mirror itself, the spider is heated to 20 degrees. But like just a few millimeters above it, we have the X-ray baffle, and that's at minus 45 degrees. And because the baffle is what's seeing directly, it's the colder space. But the nice thing is that we have a tremendous amount of work always when we design these optics to do a lot of thermal calculations. How will it behave? And because we also did tests of how does the optical quality of, for example, the eROSITA mirror or Einstein Probe mirror, if we cool it down, it's going to really degrade a lot. So that we know in case things do change, by how much will it change.
Okay, that's great to know. Another maybe naive question, but I'm just curious because of your vast experience from all kinds of optics. How do you envision the future of hard X-ray optics? So I know only about NewStar, right, with the slump class with few arc minutes, PSF. But is there some kind of new technology or coating one could use to boost the focusing?
The thing is, you will always be using coatings.
Yeah.
If you want to really get a big effective area, high energies. But the problem is, coatings always also have the negative side of degrading the surface quality of it. So if you're able to design a way for coating which will keep a perfect mirror shape and keep the shape after the coating, then you have a good chance of getting a high spatial resolution. Of course, the other way you can do it is use simple coatings, but have very long focal lengths.
Yes, of course. Yeah.
But having very long focal lengths means that your angles will be very small, and it means you need lots of mirrors parallel or mirror modules mounted parallel to one another, so that you can get more effective area. Because basically, each mirror only integrates a tiny ring. So then the next mirror integrates the next ring, and so on. And so that's really the art of finding the best compromise to get the best results.
That would be also complicated to launch such a
I don't think so, but if we're talking about 20 meters, you can
Yeah.
either build a mast and
Yeah,
or something.
like new star. Yeah. Okay, thank you. Any more questions?
Thank you for your patience.
Thank you for the very wonderful talk, and thank you for enlightening us on X-ray optics calibration and testing. Thanks a lot.
Right.